Look, I'm just a geologist. I like rocks. I love rocks.
So yeah, to segue into the topic for today, Bill is going to be talking about some climate change stuff today. So Bill, what's your research involve? What do you do? Who
so
are
I
you?
do. I'm just a guy, man.
State your purpose.
So I study paleoclimatology, which is the climate history of the Earth. Specifically, and that's like the bulk of what I do. We all have little tangential things also, but the main purpose is to study what climate systems used to be and what drove those systems and what their effects were in the past. And more I'm trying to focus my research so that it informs us on where we're going in the future. So it's really all surrounding one basic principle, like the motivating principle, and that's right now. We're working on doubling CO2 levels from pre-industrial times.
You're trying to double them.
Yeah, we are getting pretty close. Like we're just ramping up the amount of CO2, but we've only been doing this since working on 200 years or so. Like 1790 might be the earliest start of the big increases in CO2, but really much of it's happened since 1960, and that's not enough time for the climate system to really respond and reach equilibrium. This is the trickle down effects and the spillovers required in a minimum centuries and typically thousands of years to respond. And so we've just let the valve off, and we don't know what's going to happen exactly, and we're trying to figure that out. And so my colleagues and I look into the past when multiple independent proxies or techniques will tell us CO2 was at least as high as it is now. Okay, well then what did the climate look like in those conditions after, there had been many thousands to millions of years to respond and get used to those higher CO2 levels.
So what techniques do you do to with your paleoclimate research?
Good question. So I use two major approaches. My bread and butter is to use fossil soils, paleosols, which I think you guys have an archived episode that covers way in the back.
A little bit. So why just in case the listeners haven't heard that, what in 30 seconds or less, what's a paleosol?
A paleosol is a fossilized land surface. So it's a landscape that extinct animals used to walk around on, extinct plants used to grow in, and it's encapsulated in the rock record as a rock now. And it retains a lot of the chemical and physical and visible appearances and structures and signatures that it used to have. So a paleosol will tell you a lot of information that it was starting to record when it was a soil actively forming on the Earth's surface.
And also you do, well, what, I guess, how can I phrase this? So what are you exactly looking for with this paleoclimate data? Like what's, I guess, if there's like one thing that you can find, what would that be for you?
The big thing that's captured my attention over the last couple of years is the hydrologic cycle and questions like how much did it rain?
Okay.
If CO2 is higher, is it going to get wetter or drier?
Now, just for us paleosol / soil dummies out there, can you? We basically look at modern soils, figure out, it rains this much every year in this soil for as long as we know, and we measure all the constituents of this soil, all the way it looks, the chemicals that it retains, the chemicals that leave it, and then what? You apply that knowledge to the old dirt?
Yep. That's exactly it. And you can do it in a lot of different ways. Just from a real basic sense, any of us could do this. I live in Virginia right now. A lot of the soils here are reds, browns, and grays. But if you go out to Arizona, the soils are really pale because they have a lot of calcite in them. the mineral calcium carbonate, which as geologists, it's like our best friend, really common mineral. There is no calcium carbonate that's actively forming in the soils in my yard. The bedrock is made of it, and that stuff dissolves really quick. But a mineral like calcite will tell us a lot about climate conditions. It's actively forming in California, Arizona, essentially the arid West, generally speaking, because there isn't as much water as over here. So, water loss drives carbonate formation.
Cool.
So that's just one sense. You can just see it in the color.
Yeah. Sorry for that digression, but carry on.
Yeah. The big questions that I'm seeking right now are the rainfall questions. I've been applying that in the Great Plains. This is a great environment to ask that kind of a question because it's where we grow all of our breakfast cereal and our oats and all the corn that goes into almost every product Americans eat and drink.
Last summer I drove past the Lucky Charms field.
Ooh.
There you go.
Yeah.
Leprechauns just pollinating it,
How does a leprechaun pollinate?
Is this going to be a biology podcast?
Yeah, that's for the biologists.
Yeah.
Yeah.
So, Bill, with your research, what's one of the most striking findings that you found?
It's a cool question. I would say that I've found a few striking findings that echo into the void. I find them to be striking. So one thing is there's very, very little information for past the recent past, meaning the last few million years, of what the climate was like in the mid-continent in the Great Plains. And that's because there really aren't many rocks that formed during that interval of time and were buried and preserved and are now visible at the Earth's surface. It's just very, very rare. Most of the rocks are from the Cretaceous, from the Western Interior Seaway across much of the Great Plains. And then there's some beautiful little nuggets like the Badlands National Park and the White River Group there. That's from the Eocene and Oligocene. That's several tens of millions of years ago. Different animals were around. There wasn't a permanent ice sheet on Antarctica for parts of that time. So you can't compare it to today. Now we have found some areas that are 4 to 3 million years old and some younger that we can apply these methods to by looking at paleosols that are 3-4 million years old. And we found we were testing hypotheses like, okay, 3 to 4 million years ago, did it rain more or did it rain less? And the striking thing that we found is there's abundant evidence to say that it rained more. And this was at a time when CO2 levels were about 400 ppm, which is where we're at now. We're cruising past, but it was an equilibrated climate. And so this helps to answer the question, all right, all things held equal, when we run out of groundwater in the Ogallala Aquifer, are we, how deep is the crap that we're going to be in? Like, how bad is it going to be?
So why, for the listeners that may not know, that aquifer, the Ogallala Aquifer you just mentioned, why is that so important?
Oh, it's the primary water source for most of the agriculture that we depend on in this country.
So if that dries up, it's not going to be good for farmers, right?
And it's not drying up naturally. We humans are pumping the crap out of it. And my understanding, I'm not an expert in this at all. My understanding is a lot of that water was recharged, tens of thousands to maybe a million years ago, but from the glacial, interglacial cycles, I would imagine. It's not very old water.
Yeah, no, you're pulling, some of the water, the youngest water you're pulling up is probably, 15,000 years old or something like that.
Baby
water. It takes a while to fill up.
Yeah.
Baby water.
Baby water.
Yeah,
I mean, that's the youngest. So it's all older basically than that.
Yeah, and it's a huge environmental issue out there in the Midwest United States. Like Bill said, so many farmers are dependent on pumping water from that aquifer to water their crops. And if that thing goes dry, that's it. Like it doesn't come back very fast. And, some of the stuff takes tens of thousands of years to refill.
And and that's not even factoring in, say, subsidence, where if you draw down too much, the overburden starts collapsing and closing off that pore space that will never refill then, because you're drawing down too much. That's the big deal out in like the Imperial Valley of California. They're drawn down
you
so
squeeze
much.
that sponge and then it doesn't let go, so no water can fill back in.
That's a good
For
analogy.
the lay person.
There you go. That's pretty good.
This
pretty
guy.
Good.
Yeah.
It's a great analogy. Yeah.
Here's a question I'm just thinking off the top of my head. So, the Great Plains, you're not under ice there until, the upper Midwest, like the tongue, you have into like Wisconsin of the glacier. But like Nebraska, which you're familiar with, why don't, even if it's like dry, why aren't you forming soil then? Or has it been eroded, or is it too dry? Or answer me.
Yes, sir.
Or is it buried?
Is it
there's a significant amount of sediment bypass that occurs, and also long-term erosion. And so you do get deposition in limited areas, but that sediment gets reworked then, so it doesn't stay within the Great Plains. It's a big tributary system that's
it's just
just draining down.
Right. And if it doesn't stay there, you're basically resetting your clock
every time. You get a big flood every time.
The sediment's being stored on floodplain terraces and minor alluvial fans. Anyone who's interested in that, there's a great paper that's online now by Anthony Lazell in GSA Bulletin.
I thought you were going to say podcast. So I was going to be like, Bill.
No.
Come on. There's only one geology podcast, right? The only one that
This
matters.
American Life just covered it, guys. Come on.
Oh, yeah. They also, the first year, this is a digression, the first year the Pulitzer gave out an audio reporting Pulitzer Prize, and This American, they snubbed us yet again. This American Life won the Pulitzer for...
Well, they're setting precedent. Now you guys are in the running for next year.
This could be the episode that gets us.
I believe it will.
There's dramatic tension in these pauses.
Sorry. Anyway, flooding terraces and alluvial fans.
Yes. Sorry. And please say that name of that paper again. Sorry.
Oh yeah. So it's by Layzell, Anthony Lazell and Rolf Mendel from the University of Kansas, KU. And it's in GSA Bulletin, the Bulletin of the Geological Society of America.
Very cool.
Yeah, so we could link to it or something.
I was just going to say, if we can find a link, we'll post it on our website.